This presentation on basic hydraulic principles, the first in a series of video training programs, provides a comprehensive introduction to hydraulics. Hi, I'm Paul Cook for Vickers. Hydraulics, like many branches of engineering, is both ancient and modern. You've all seen a water wheel, for example, which precedes written history. Obviously, though, the use of fluids as a means of transmitting power has had its greatest development in the past 50 years. Hydraulics is the transmission of power through the use of confined fluids. And it's based upon a principle discovered by a Frenchman, Blaise Pascal, during the 17th century. Pascal's law states that pressure applied on a confined fluid is transmitted undiminished in all directions and acts with equal force on all equal areas. Here, let me show you. The classic demonstration of this principle is to fill a small neck jug with fluid and then burst it by applying pressure on the cork. But rather than make a mess here, a more practical example is to show two pistons, one large and one small, interconnected by a pipe or tube and filled with fluid. A large weight on the bigger piston can be balanced by a smaller weight on the little one. To understand this better, let's assume an area of 10 square inches on the large piston and 1 square inch on the other. Now, since every action has an equal but opposite reaction, let's place a weight of 100 pounds on the large piston. This, of course, will require a force of 100 pounds to support it. This force, spread over the 10 square inch bottom of the piston, will amount to 10 pounds on each square inch, or a pressure of 10 psi on the fluid. According to Pascal, that pressure will be exerting a 10-pound upward force on the 1 square inch area of the small piston, which can be balanced by a 10-pound weight on its top. Now, before you start thinking we've gained something for nothing, let's push the small piston down a distance of 10 inches. This will displace 10 cubic inches of fluid, which in turn will force the large piston upward. The large piston, because of its 10 square inch area, will only rise 1 inch. Like its mechanical counterpart, the lever, what we gained in force was lost in distance. So you see, you can never get something for nothing, not even in a hydraulic system. But we can perform efficient work. Basically, there are two motions we can achieve hydraulically. We can move something in a straight line, or we can make something rotate. A cylinder or linear actuator provides the straight line motion. It can be single acting like a hydraulic jack where the weight of the car brings it back down, or double acting where the piston is forced both forward and backward in its bore by fluid under pressure. A rod connected to one side of the piston extends from one end of the cylinder to the part to be moved. Now, here's another point to remember. The force exerted by a cylinder depends on its area and the pressure that's applied. Force equals pressure times area. Since the rod reduces the effective area of the piston, the force available when retracting a piston will be less than it is on the forward stroke. The rod, however, will partially fill the cylinder. So less fluid and proportionately less time will be required for retracting than for extending. Here again, what's gained in force is lost in speed or distance. Now, the second basic motion we can achieve hydraulically, rotary motion, usually calls for hydraulic motors. Motors come in a wide variety of sizes and shapes, from tiny ones which provide only a few pound-inches of torque to huge models which develop literally thousands of pound-feet and can flip over a boxcar with ease. The most common motors, and pumps for that matter, are vane, piston, and gear type. But since the functions of all three motors are the same, we'll just use the ANSI symbol to represent them. A motor is driven by the fluid. With pump flow connected to this port, the motor would rotate in this direction, provided, of course, that we have something to drive the pump. Our drive could be a diesel or a gasoline engine, an electric motor, or even a windmill. But for now, let's settle for an electric motor. Now, you might be asking yourself, why bother with a hydraulic motor if you still need an electric motor? But bear with me. As good as they are, electric motors do have certain limitations. Most run at a constant speed, let's say of 1200 RPM. Then too, they usually turn in only one direction. And finally, we all know what happens if you stall one. If you're lucky, you'll only blow a fuse. If you're unlucky, the motor burns out. Now, with an electric motor driving our pump, let's see what happens with a hydraulic motor. Since it's a positive displacement unit, if it were to stall, it would not accept any more oil. The pump, also positive displacement, would stall too, since its outlet would be blocked. This in turn would stall our electric motor. Oh, you say, wait a minute. Let's put a relief valve in this line. A relief valve doesn't have to be anything more than a ball held on a seat by a spring. You just tighten up on the spring until it's harder to push the ball off its seat than it is to drive the motor with its normal load. Overloading the motor would cause the ball to lift off its seat and divert the pump flow back to the tank, permitting the pump and electric motor to run even though the hydraulic motor is stalled. Okay then, what if we direct the pump flow into this port, the opposite one? It will rotate the motor in the opposite way, right? Right. But instead of repiping our circuit to change direction, let's just add another valve. This one, a directional valve. We'll run a line from this port to one side of the motor and from here to the other side. Now, with the pump connected into here, we can flip this handle and direct flow into either side of the motor. Of course, there will be flow out of the opposite side, which we'll pipe back to the reservoir through this, the fourth port in our directional valve. Now that we've got a handle on the basic hydraulic circuit, let's try a little arithmetic. Let's assume that the displacement of the pump is the same as the displacement of the hydraulic motor. This means that in one revolution of the pump, there is enough fluid put out to drive the motor one revolution. With the electric motor driving the pump at 1200 RPM, the hydraulic motor will also run at 1200 RPM, neglecting a little internal leakage since nothing's perfect. Now, let's cut the pump size in half, say from 10 to 5 gallons per minute. You got it. The 10 GPM motor would run at 600 RPM. Rather than change the pump to change the motor speed, let's install a flow control valve. It has an adjustable opening we can set to pass any portion of the pump delivery. At 5 gallons per minute, the motor would turn at 600 RPM. Increasing or decreasing its speed is just a matter of increasing or decreasing the size of the flow control orifice. Now, I'd better point out that pump flow, which does not go through the flow control valve, returns to tank through the relief valve at its setting. And that wastes energy. Looking at the brighter side, though, that same fluid could be used to perform other operations on our circuit at the same time. So another advantage of using hydraulics is the ability to use a single power source and perform several different functions simultaneously. Now let's take a minute to recap what we've done. We started with an electric motor which ran at a constant speed in one direction and could not be stalled. We now have a hydraulic motor which can be run at infinitely variable speeds in either direction and stalled under load without damage. We did it with only 3 valves, a directional control, a flow control, and a pressure control, also known as a relief valve. You've probably already realized that these same components would enable a cylinder to function in essentially the same way as a motor. In fact, these components are the main ingredients of even the most complicated systems. By now, you're probably thinking this hydraulic stuff is pretty simple, and you're right. Before you start out on your own, however, there are a few more things you should know. Oil is still the fluid most commonly used, but as slick as it is, it still takes some effort to push it through a line. I know that's the pump's job, but we want to make it as easy as possible. Did you know that when you double the diameter of a pipe or tube, you increase the area 4 times? Perhaps it's more important to know that a tube half the diameter of the original one would have only 1/4 the area. That means the same amount of fluid would have to move 4 times as fast through it, and the friction would increase proportionally. Now, what does this mean in practical applications? If you must replace a line, use the same size or a little larger, and avoid as many elbows and bends as possible. Another thing, a surprising number of people think a pump sucks the oil out of the reservoir. It doesn't. A pump merely lowers the pressure at its inlet, and fluid is pushed in by the atmospheric pressure acting on its surface. Inlet lines are especially important because with only 14.7 pounds per square inch doing the pushing, any restrictions or even too thick an oil may cause the pump to starve. The technical word for this starving is cavitation, and it causes an erosion-type damage within the pump. An air leak at the inlet causes similar problems. Here, let me demonstrate cavitation by restricting the pump inlet. This is the normal sound level. This is cavitation. Well, enough of that. Too often people think that a pump pumps pressure, and that's not only wrong, it's downright misleading. I say that because the pump gets blamed whenever you can't build up enough pressure, and that isn't even the pump's job. All the pump is supposed to do is make the oil flow. Pressure is caused by resistance to flow. If you don't have enough pressure to do the job, it's usually because the oil has found an easier way to get back to the reservoir. Next time someone has this problem, find out where the oil is going, and you'll be a hero. Here's another clue. If a cylinder stops or even slows down, either you're not putting as much oil into it as you were, or it's leaking past the piston. To find out if oil is leaking past the piston, block the cylinder so it can't move, and remove the opposite line. Then turn on the pump and direct oil into the line that is still connected to the cylinder. So if oil flows out of the other cylinder port, you've got a leaky piston. But before you remove the opposite line, be sure it is the opposite line, not the one under pressure, or you'll be sorry. Seriously though, be very careful in removing any hydraulic line. Be sure it doesn't go to a cylinder or a motor that's supporting a load. If it does, either lower the load or support it so that it can't fall. An accumulator, too, stores oil under pressure, even with a machine shut down. If you're unsure about it, find someone who knows before touching a thing. I suppose you already know that increasing the relief setting doesn't increase the speed of a cylinder or motor. It's the amount of oil available and the size of the actuator that determines speed. That's why little cylinders move faster than big ones in the same system. Increasing the pressure will let you clamp tighter or move a heavier load. But be sure you don't try to exceed what the system is designed to do. Back at the start of this discussion, we used an electric motor to drive a pump. And you may have wondered, how big a motor? To determine this, we have to know how much force or torque was needed to do the job. That would tell us the pressure required and the size of the actuator. Then, knowing how fast the actuator had to move, we could determine the amount of fluid in gallons per minute that would be needed. Well, we have a formula to determine the horsepower required to move a given flow rate at a known pressure. You may want to make note of it. Horsepower equals gallons per minute times pounds per square inch times 0.000583. That 0.000583 is a constant. It's the horsepower required to move 1 gallon per minute at 1 pound per square inch. Actually, this formula tells us horsepower output of the pump if the pump were 100% efficient. It would also be the input horsepower required to drive it. Unfortunately, pumps aren't 100% efficient. In fact, few things are. We would probably be safe in assuming that a well-designed pump in good condition should be between 80% and 90% efficient. The electric motor size, or input horsepower, requires that we include pump efficiency in our formula as follows. Horsepower equals gallons per minute times pounds per square inch times 0.000583 divided by pump efficiency. Well, that wraps up the first in our series of video training programs, Basic Hydraulic Principles. If we haven't overloaded your sensory capacitors with too much information too fast, and if you combine what you've learned today with plenty of good common sense, you have the basic ingredients to become a first-rate hydraulics person. Thanks for your attention. I'm Paul Cook for Vickers.